Welcome to qnawire.
For part A of the given problem, the lowest level is for n is equal to 1. So E1 is equal to 1 times h squared, which is 6.626 times 10 to the power minus 34 joules a second squared, divided by 8 times the mass, which is 0.20 kg, times L, which is 1.3 meters squared. This gives us 1.6 times 10 to the power minus 67 joules. For part B of the problem, the velocity that corresponds to this energy can be found by using energy E is equal to 1 over 2 mv squared. From here, V will be equal to square root of 2 times of energy divided by mass. Plug in the value for energy, so 2 into 1.6 times 10 to the power minus 67 joules divided by 0.20 kg. This gives us a V to be 1.3 times 10 to the power minus 33 meter per second. If the ball has this speed, the time it would take to travel from one side of the table to another will be simply t is equal to 1.3 meter divided by v, which is 1.3 times 10 to the power minus 33 meter per second. This will give us a time of 1 times 10 to the power plus 33 second. For part C of the problem, E1 is equal to h squared divided by 8ml squared. E2 is then 4 times of E1, so delta E is equal to 3E1, which we can write 3 into 1.6 times 10 to the power minus 67 joules. This will give us a delta E of 4.9 times 10 to the power minus 67 joules. For part B of the problem, the answer is no. Quantum mechanical effects are not important for the game of the billiards. The discrete quantized nature of the energy level is completely unobservable.